Hi everyone, here is a video to go through the calculations from the gas over water lab. I'm going to be using this data that's recorded right here, so your numbers of course will be a little bit different unless your data is exactly the same. So first question, calculate the partial pressure of hydrogen gas collected in the graduated cylinder. So remember that in this lab, we were collecting gas from this reaction in this graduated cylinder. So we had the gas that was produced, but because water was in this graduated cylinder, we also had water vapor in that, that mixture of gas. So the total pressure, it was equal to the pressure from the hydrogen gas that was produced plus the pressure from the water vapor, okay? The total pressure inside there is just the same as the atmospheric pressure. I recorded that as 0.82 atmospheres. The pressure of the hydrogen gas, the partial pressure of that is what we're looking for. And the pressure of the water vapor, I can use my water vapor chart to find. So I'm in atmospheres, so I want to use atmospheres. My temperature of the water was 22 degrees. I want to use that temperature because that determines how much vapor there is, not the temperature of the room. The temperature of the water determines how much water vapor there is. So I'm going to go to 22 degrees Celsius and look at my atmospheric pressure. I have 0.026 atmospheres of water vapor pressure at that point. All right. Now this is just a simple algebraic problem. When I solve for the pressure of the hydrogen, partial pressure of the hydrogen, I get 0.794 atm. Okay, the second question asks me to calculate the volume that 1 mole of gas would occupy at the current pressure and temperature of this room. Remember that the 22.4 moles per liter, which we use in stoichiometry calculations, is only at STP, standard temperature and pressure. We are not at standard pressure and we're not at standard temperature either. So we have to calculate the amount of space that 1 mole would take up so that we can use it in this calculation down here. So I have a set of conditions. I'm not changing conditions. I have a set of conditions and I'm solving for the unknown volume. So when I have a set of conditions and I just have one unknown, I use my ideal gas law. My pressure is the pressure of the room, so that's 0.82 atmospheres. Volume is what I'm solving for. Number of moles is 1.0000, R 0.0821, and temperature is 24 degrees Celsius. So when I convert that to Kelvin, I get 297.15 Kelvin. Okay, again, simple algebra. I get that my volume is equal to 30.725 liters. All right, now calculate the theoretical yield of hydrogen gas that could be produced from the specific amount of reactants you use in the experiment. Okay, so remember, theoretical yield is how much could we make if this reaction went perfectly. But remember that we might have one reactant that runs out before the other reactant, and so we'll have leftover of either the magnesium or the hydrochloric acid. So we need to figure out which one runs out first and how much hydrogen gas we can make from that, and that will be our theoretical yield. So let's first figure out how much hydrogen gas I can make from magnesium. I started with 0.14 grams of magnesium. And I know that when I go from one substance to another, like the amount that another would make, I need to use stoichiometry. So I need to convert from grams of magnesium to moles of magnesium because the moles of magnesium, the mole-to-mole ratio is what my equation gives me, not a gram-to-gram ratio. So I'm going to go from grams of magnesium to moles of magnesium. And then I can go from moles of magnesium to moles of the product that I'm interested in, which is H2. And then it asks me to find the theoretical yield in the volume of hydrogen gas. So I'm going to go then from moles of hydrogen gas to liters of hydrogen gas. And that's why I had to calculate this right here so I would know how many liters are in 1 mole. Okay, so let's fill in these conversion factors. In 1 mole of magnesium, how many grams do I have? That comes from my periodic table. So here's magnesium, 24.3050 grams of magnesium. Okay, then this mole-to-mole ratio comes from my chemical equation, which you should have written down as magnesium plus hydrochloric acid produces hydrogen gas plus magnesium chloride. And when we balance that, we get this. So the mole to mole ratio is 1 mole of magnesium produces 1 mole of H2. And then 1 mole of H2 occupies how much space? That's what we just figured out up here. It occupies 30.725 liters. So when I multiply that out, I get 0.18 liters of hydrogen gas. So if all of my magnesium was used, this is how much hydrogen gas I could produce. Now let's see about if all my hydrochloric acid was used. Well, I started with 9.98 milliliters. I'm going to convert from milliliters to liters, from liters to moles using my molarity, because I know that my solution had 0.5 moles per liter. And then I want to go from moles of HCl to moles of H2. Well, my equation tells me that for every 2 moles of HCl, I have 1 mole of H2. And then I want to go from moles of H2 to liters of H2. And that's this calculation again. So in 1 mole of H2, I have 30.725 liters of H2. Okay, so when I multiply that out, I get 0.077 liters of H2. Okay, so this one could make more H2, this one could make less H2. Which one's going to run out first? Well, the one that can make less. And so if it runs out first, we're actually going to have extra of this. We're not going to be able to make this much H2 because we don't have enough other stuff. This one runs out first. This is our theoretical yield. So I'm going to put a box around that and label it as my theoretical yield. Now it asks me to calculate the percent yield for my reaction. Remember, that's how much did you actually make, so actual yield, over how much you calculated that you theoretically could have made, so theoretical yield. And then that's a percentage, so you're going to multiply that by 100%. Okay, so my actual yield was, of hydrogen gas, 73 milliliters. My theoretical yield is in liters. Those units need to match on the top and the bottom so that they cancel out. So I'm just going to convert 73 milliliters for my actual yield into liters. So I know that in 1 liter there are 1,000 milliliters. So that's going to give me 0.073 milliliters was my actual yield. So then my percent yield is that number, my actual yield, 0.073 mils. I'm sorry. The units on that should be liters because I just converted it to liters. So 0.073 liters divided by 0.077 liters, then my liters canceled out, times 100, and the percent that I get is 95% yield of hydrogen gas. All right. Now, I'm not going to tell you how to do the CER, but read the question carefully. A lot of people didn't even answer the right question. It says, what is the partial pressure of the hydrogen gas collected over water in this experiment? That was from question 1. Calculate the partial pressure of hydrogen gas collected in the graduated cylinder. Okay, you're explaining this answer here. A lot of people, for some reason, explain the percent yield. You're explaining the partial pressure of the hydrogen gas in your CER. All right, thanks for watching.